Hello student, in this video we are going to learn about a comparators. So what is meant by comparator? Comparator, it is a device or a precision instrument used to compare your dimension of a given component, given workpiece with the working standards. So when we are comparing our device with the standard component, then that particular instrument, by using that instrument, whatever we are doing the process, that is called as a comparator. So comparator, it is a device which is used to compare a dimension of your workpiece with the standard workpiece. So comparator is does not going to indicate the actual dimension, remember. So but it indicate how much deviation of your workpiece dimensions are there with the standard one. Only how much deviation is there in your workpiece as compared to the standard, it is showing that value only. In mass production, identical components are produced on a very large scale. All of you know mass production is for only a large scale component. So your general instruments like vernier caliper, micrometer are not feasible for use because it requires more skill for measurement. So that time the comparators are used to compare your dimension with the standard one. So how they are classified? So first type of comparator is mechanical comparator. It works on the different components like gears, pinion, different springs, levers, linkages. The pneumatic comparators, it is basically uses a air pressure to measure the deviation. Then optical comparators are there by using lenses, light source, mirrors. We are going to find the deviation. The electrical comparators are there which works by using setup, set down transformers. Then electronic comparators are there, some amplifiers, digital signals are used, and combined comparators are there. So any combination of two we can use here. So in this we are going to see first four types: mechanical, pneumatic, optical and electrical comparator. So mechanical comparator again divided into the four types. First is the dial indicator, Johansson Mikrokator, Sigma comparator and mechanical optical comparator. So these are four types basically we are going to study: dial indicator, reed type comparator, Sigma and Johnson's Mikrokator. So what is a dial indicator? Generally a dial indicator operates on the principle that a very slight upward pressure on the spindle at a point of contact is multiplied through a system of gears and levers. So generally I will show you. You can see this figure of dial indicator. Just wait. Okay. This is a diagram of dial indicator. So you can see the figure of dial indicator here. So if we go next slide, now you can see here this is a dial indicator. It is having the graduation on the circumference, you can see, and at the downward side this is a plunger. So when plunger is moving up and down, this needle will deflect and it will show the variation. Okay. So initially what we have to do, we have to set the dial indicator with the standard length, then 0 is set and then the measurement is done. So how it is done? We can see, suppose I want to check a parallelism of surface. So how it can be checked? You can see the dial indicator is placed on this flat surface and it is moved from one end to another end. And then if needle deflects, then it indicates that the surface is not parallel. If needle remains at particular position, then we can say that your surface is perfectly flat. Also, if I want to check the perpendicularity or roundness, you can see here dial indicator is placed horizontally, plunger is touching to this round bar which is rotating. So simultaneously you can check the roundness or perpendicularity. So as needle is moving, so it is not perfectly round. Likewise, variation we can study. So also the flatness of your surface can be checked by the dial indicator. You can see if needle is moving, then it indicates that your surface is not perfectly flat. Also a roundness, perpendicularity, straightness we can check with the help of dial indicator. So by comparing two heights or distance between two narrow limits, we can use dial indicator to determine errors in geometrical forms such as ovality, roundness, taper. We can check with the help of dial indicator. So likewise, these are some applications of dial indicator. Next is Johnson's microkator. You can see the diagram of this Johnson's microkator is consisting of two elbows. These two grey color elbows are there. In between the elbows, a plunger is placed, which is supported by the slit washer, so that plunger will exactly move in the vertical direction with the help of the slit washer. There is a frictionless arrangement is there. This plunger is connected to the another end to the bell crank lever. You can see which is moving. Moved portion is shown by a dotted arrow. It is connected to the twisted strip or twisted spring. It is connected to the another end with the help of cantilever strip, and whenever plunger is moving upward, so this is a dotted portion, you can see that it will deflect this bell crank lever on the right hand side, and due to that this twisted metallic strip or spring, it will elongates or it will move on the right hand side, so that a pointer is placed on this strip, it will deflect. So we'll see one small video. Listen carefully.
Hello everyone. In this Mikrokator, this is a type of mechanical comparator which was developed by the Johansson Ltd company of USA. This instrument uses principle referred as Abramson moment, named after H. Abramson, to obtain high mechanical magnification of the difference in length as compared to the standard. A twisted thin metal strip holds a pointer, which shows the readings on the suitable scale. Since there is no friction involved in the transfer of movement from the strip to the pointer, it is free from backlash. Let us see its construction. The metal strip is twisted and fixed between the two ends as shown. Any longitudinal movement in either direction will cause the central portion of the strip to rotate. One end of the strip is fixed to the adjustable cantilever and the other end is fixed to the spring elbow. The spring elbow, which consists of a flexible strip and a stiff diagonal, acts as a bell crank lever and causes the twisted strip to change its length whenever there is a movement in the plunger. The change in the length will result in a proportional amount of twist of metallic strip. The magnification can be varied by changing the length of the spring elbow. A pull on the metal strip subjects it to tensile force. In order to prevent excessive stress on the central portion of the metal strip, perforations are made in the strip. The plunger rotational movement is arrested by the split washer, which only allows vertical movement of the plunger. Since we understood the construction, now we will see how it is used to compare or its working. The instrument is initially calibrated to the standard and the 0 is set to this value. Instrument also has two pointers which can be set as upper and lower limits. Then the test specimen is placed on the measuring table and made to slide below the plunger of the instrument. Any difference in the measured dimension of the specimen will result in either lowering or rising of the plunger. The lowering and rising of the plunger will make the bell crank lever to move in forward or backward direction, and in turn will twist or untwist the metallic strip.
Okay, so this is how the Johnson's Mikrokator works. So again we will see. You can see you have seen this animation. So initially what happens, we have to set the standard value to the Johnson's Mikrokator. So this is at the center, plunger is there. This plunger is set on the standard first. You can see the standard is placed first at the below to the plunger, and then 0 is set, and then standard is removed and your workpiece is placed below the plunger, and plunger is allowed to move from one end to the another end. That time, due to the uneven surface of your workpiece, this plunger will move up and down due to this uneven surface, and that due to movement of plunger, this bell crank lever will move either downward or either upward. So you can see this movement of bell crank lever here, and due to that movement of bell crank lever, this twisted metallic strip is there at the center. Okay, so it will elongates, or length will increase or decrease. So due to that, your plunger will move on the calibrated scale. So here you can see minus 10, 10 is written, plus 10 is written. So it is my lower limit and upper limit. Your plungers or your pointer should move between that 2 point only. If it is moving outside the point, your job is not acceptable. So this is the tolerance zone is given, minus 10 to 10. So like this Johnson's microkator works. So this is how it looks like. Principle is given. So remaining part we'll see in the next video. Thank you.